Now here's our first theorem that's going to compare a Cauchy sequence to a convergent sequence. The theorem says every convergent sequence is a Cauchy sequence. So another way of writing that using if-then, or an implication, P implies Q, would be if A sub n is a convergent sequence, then A sub n is a Cauchy sequence. So our proof is going to start off by saying let A sub n be a convergent sequence. And since it's a convergent sequence, we need to define what the limit of the sequence is. Since it's convergent, we know this real number here exists, capital A. Now to prove that a sequence is Cauchy, similar to proving one is convergent, we need to begin with an arbitrarily chosen epsilon. So, to prove that this sequence is Cauchy, let epsilon greater than 0 be given. And what are we going to have to do? You have to look back at the definition of a Cauchy sequence. We're going to have to find a capital N, which will be an index into the AN sequence, such that any two elements in the sequence from that point on, from A capital N on, any pair of them, when you take the difference or distance between them, it's going to be less than this chosen value of epsilon. Okay, well, let's take into consideration that A is the limit of the sequence. Therefore, I can say, let n be a natural number. Let that be such that little n greater than capital N implies AN minus the limit is less than epsilon. Actually, let me make that epsilon over 2. If you want to write the justification for that in brackets here, I'm allowed to do that because AN goes to A, capital A. Capital A is the limit of the sequence, so I know that this capital N exists. And it turns out I'm going to use that capital N for the definition, or for proving that it's a Cauchy sequence as well. Okay, so we've got this capital N defined. Thus, if we take M and N, two numbers greater than capital N, and by the way, this N is not the same as this one. This is kind of a dummy variable used for the definition. I could actually turn this into an L or something like that, and that into an L. This is two arbitrarily chosen numbers that are greater than or equal to capital N. That implies two things. It implies that AN minus A in absolute values is less than epsilon, and it also implies that AM minus A is less than epsilon. After all, we've got two numbers that are at capital N or beyond or bigger, and we know that the sequence converges to A, so we're just using the definition here. And actually, I can finish up the proof with the next line in a little bit of algebra. I'll say therefore. Let's see. For a Cauchy sequence, I want this. And I need to show algebraically that this distance is less than epsilon. Well, we're going to write this as an equality that's just a simple, I just added 0. I didn't change it at all. I subtracted A and I added A. So by arithmetic, those two expressions are equal. And then I'm going to use the next step, I'm going to use the triangle inequality. It says this. That's the triangle inequality using this term and this term. Now you might notice I reversed the A minus AM became AM minus A, but that doesn't change. Just the property of absolute values allow us to make that. So the triangle inequality is why I did that step. which would allow me to do that. But I know that an minus a is less than epsilon over 2. Rewrite this. I forgot to put epsilon over 2 right here in both cases because of this. And that's less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So we have shown that the distance between a and am for any m and n greater than capital N is less than, strictly less than, epsilon, and that completes the proof. That proves that the sequence an is Cauchy.